Hi everyone, I welcome you all in the next lecture of stoichiometry and process calculation lecture. So in the previous lecture already I have described about the steps of solving the material balance problem, and where we have seen there are various steps, and before that also I have discussed about how to calculate the degree of freedom, and that basically tells you whether the problem is solvable or not with the given data and with the given equation, right? So if you'll go through that lecture, definitely you'll be able to understand all that problem. So in today's lecture, I'll be talking about the metal balance without chemical reaction. So in my previous lecture also, I have categorized the metal balance problem in metal balance when there is a chemical reaction, and when metal balance involves without chemical reaction. So here we are going to understand about the metal balance without chemical reaction, right? So when we talk about the material balance calculation, it's very important in the design and analysis of various separation operation. So if you see in a real process industry, so the preliminary treatment with the raw materials are very important before it is being subjected to either in a reaction vessel or in a distillation column or in an absorption column. And also the product that is leaving from the reaction vessel or from the distillation column or from absorption column, that requires treatment for the purification, separation, and for the recovery of the byproduct. Okay, so these separation techniques are also very important, or it's employed to give definite properties of the product to render the product in a form of suitable for packaging, handling, and to reduce the cost of transportation and product. So before we embark on the solution of the material balance problem, we will briefly discuss the salient feature of some of the important separation methods like evaporation, crystallization, absorption, distillation, and we'll try to understand the better understanding of material balance system. So here, first, I'll be talking about the evaporator unit that does not require any chemical reaction. So if we see that, even though if you see, I have already made evaporator lecture on the evaporator. If you go to my YouTube channel, so there in heat transfer section, I have already made these things. But here, that this subject requires the discussion of evaporator that involves there is no chemical reaction for the material balance. So that's why I am going to discuss here. So if I talk about the evaporator unit, so first problem that I am going to discuss, problem on evaporator. So I won't be talking about the energy balance, only I'll be talking about the material balance. In the energy balance section, I'll be talking about the energy balance on the evaporator as well. And energy balance is also very important to calculate some important parameter for the evaporation unit. Right, so let's say this one is the evaporator, and you add a feed into the evaporator, and from the top you will see there is a vapor, and from the bottom you will see the liquid, right? So, and then there is a stream also, so there will be a stream m dot s, and then lambda s will be the stream. So if we perform the material balance, so let's say I'm assuming that F be the feed rate in kilogram per hour. F is equals to feed rate in kilogram per hour, because evaporator unit operates at in a continuous mode. And if I'm assuming XF is the mole fraction solute in feed, and let's say here L is the liquid which is coming in the bottom of evaporator in the kilogram per hour, and V is the vapor flow rate that will be also in kilogram per hour. Is that clear? So if we perform the overall balance, so first I'll write overall material balance. So we can say that F equals to what? L plus V. That is your equation first. Now if I do the solute balance, then I can write F into XF, that is equals to L into XL plus V into XV, right? So here you will see XL, and since our vapor phase is free from solute, let's say I am assuming if vapor phase is free from solute, because only water will get evaporated, since solute, so what you will feel here, xv will be equals to 0. So in that condition you will get the equation f into xf, that is equals to L into XL. So this will be a second equation. So this is how you perform the material balance for the single effect evaporator, right? So this is called as the single effect evaporator, right? That's great. Now coming to the multiple effect evaporator, and how do we perform the material balance in multiple effect evaporator? Right. So when we talk about the multiple effect evaporator, so we have two kind of problem, either that is a forward feeding or backward feeding, right? So let's say forward feeding or backward. So here I will be discussing about the forward feeding multiple effect evaporator. In backward feeding, you can go to my YouTube lecture. There you will find a good video on that, and you can understand that thing. So basically, how does this look like? So you have a evaporator unit, let's say. Right, great. So here you are supplying a feed F in kg per hour, right? And then there will be a stream also, m dot s, and then latent heat of vaporization of a stream is there. So this is first effect, this is second effect, and this is called as the third effect. So in the first effect, what will happen, a vapor is being generated over here, and then what will happen, this vapor will come to the second effect having flow rate is, let's say, B1, and then what will happen, the liquid will be coming as a bottom here, this is L1, and then that will enter into the evaporator as a feed, right? So this will enter into the evaporator as a feed, okay? Then from the second effect, what you will see, the vapor will form as a V2, obviously, and this will work as a kind of heating source in the third effect evaporator, and then the liquid stream that is coming, that will work as a feed for the second effect evaporator. So this is your L2, and then from the third effect, the liquid that is coming is L3, and the vapor which is coming as a V3. Okay, so this is how the simple schematics looks like. Okay, so sometimes it is to the vacuum system. So basically what is happening here, so in evaporator we are removing the moisture content of water. So at the ultimate end, or at the end, you will see there is a thick liquid, and unit will be in the product, having unit is in kg per hour or something like that. Okay, so there are three effects, and we have seen there is input, there is output in all these three effects. So first I'll perform overall material balance for a triple effect evaporator. So right? Only will perform the material balance. So the amount of feed which is entering here, right, F, that will be equals to V1 plus V2 plus V3. Is that clear? Because this is the outlet from the evaporator, right? So V1 plus V2 plus V3 plus obviously your L3, right? That is the last effect. And where V1, V2, V3 are the amounts of vapor produced in the first, second, and third effect respectively. So I can say V1, V2, and V3 vapor produced in first, second, and respectively. Like now I'll perform the solute balance. So if I assume the mole fraction of solute here is xf, if it is x1 here, if it is x2, and if it is x3 here, so if I perform the solute balance for the combined system, so I can say f into xf, that is equals to L3 into x3, right? So I am assuming this is my second equation and this is first equation, right? And also if I perform the solute balance for so I can say f into xf, that is equals to L1 into x1. Let's say I'm assuming this is my equation third, and also we can say whatever amount of solute that is going, that will be coming out of the effect. So L1 into x1, that is equals to L2 into x2. This is my equation 4, and then L2 into x2, that is equals to L3 into x3. This is my equation 5, right? So this is how you can write the material balance. Now if I want to perform the material balance for the individual effect, right, right? So in individual effect, what you see, let's say this is my first effect, right? First effect. So here feed was going, vapor was coming, and then liquid is coming. So I can say F equals to V1 plus L1, right? If this is equation 6. And similarly for the second effect as well, if I see, if it is my second effect, right, in second effect you will see that L2 is coming here and V1 is coming, right? V2 is leaving, and then what? L L2 is leaving here, right? But this V1 will work as the steam kind of thing. So basically the solute balance we are doing, no? So here you can say this is sorry, this would be L1, no? This is your L1. So I can say L1 will be equals to V2 plus L2, right? And then for this is your second effect, right? And similarly for third effect you can say L2 equals to V3 plus L3, right? So this one is equation 7 and this will be your equation 8. So this is how you can write a balance using this kind of material balance problem. So here what we have observed, we have taken the single effect as well as the multiple effect. In multiple effect I have taken the forward feed evaporator, where we have observed that feed is introduced in the first effect, and we are getting the final product. This would be your final product and the last effect. So there will be backward feeding also, that you can go to my another lecture on the YouTube, and you will see that thing. So this is how we perform the material balance, but this concept should be clear. If you understand these things, then backward fitting will be also very easy for you. So we have to perform overall balance, we have to perform individual effect balance, we have to perform the individual solute balance, and then overall material balance, something like that. Okay, so this is one problem that is based on the material balance involving there is no chemical reaction. So here you have observed there is no chemical reaction. Now coming to the another problem, that is the crystallization unit. Okay, so in crystallization also, basically what we do, we try to form a solid from the liquid solution by evaporating or cooling a saturated solution. So you will be having a saturated solution, either you have to heat or you have to cool, and you are making a saturated solution. So first I'll write the definition, then we will move towards the material balance problem. So it is the process in which solid particles are formed from liquid by evaporating or cooling of a saturated solution, right? So you will be having a saturated solution, and you either heat the solution or you cool the solution, and you want to form the solid. So let's try to understand how we perform the material balance for the crystallization unit. So let's say this is the crystallization unit, and already I have discussed the salient feature of how to perform the material balance, or how do we write all these steps, right? So you have to keep all of these steps in the mind, so that it will be very easy for you to identify the variable over here. So in crystallization unit, you will be having a feed, let's say F, and the it will be in the continuous mode, or it will be in the batch mode, but here I'll be write feed in kg, right? And if I am talking about xf, that is the mole fraction of the solute in the feed, right? Then you will be having a w1, that is in also kg, and we call it as a hydrated solid or hydrated crystal, right? This is called as the hydrated, because you are forming this crystal while evaporating the water, but some amount of water that will be getting trapped in the solid, that is called as the hydrated solid. And if I am assuming x1 is the mole fraction of the solute here, w2 that will be in kg also, and that is called as the mother liquor, right? And if I am assuming the mole fraction here of the solid, or weight fraction of the solute here, is x2, and then because you are evaporating the water over here, so here w3, which is in kg, and weight fraction is x3, and this is your water. So here you will observe there is no chemical reaction happening, only physical transformation is happening. You are removing the water. In this particular problem, I am assuming that we are evaporating the water to form a hydrated crystal, and we are getting a mother liquor, right? Great. So how do we perform this material balance? So first we have to understand the overall material balance in this unit. Overall material balance. So overall material balance can be written as, I have told you, F is inlet in, and W1, W2, W3, all of these streams are coming out of the evaporator. So that will be your W1 plus W2 plus W3. That is my equation first. Second is the solute balance, let's say. So for solute balance, I can say F into XF, that is equals to W1 into X1 plus W2 into X2 plus W3 into X3. This is our equation second, right? So this is solute balance. So sometimes you can also do the solvent balance, right? In solvent balance, what you can do, you can write F into 1 minus XF, that is equals to W1 into 1 minus X1, because mole fraction of solute plus mole fraction of solvent, that will be equals to 1. So that's why 1 minus X1 will be the mole fraction of the solvent, plus W2 into 1 minus X2 plus W3 into 1 minus X3. Now when we talk about the water stream here, so if let's say the water W3 is free from solute, because W3 will stream will be solute. So what will happen? X3 will be equals to 0, right? Is that clear? So if then that particular equation will get converted into F into XF, that is equals to W1 into X1 plus W2 into X2 plus W3, and for the solvent balance it will get converted into F into 1 minus XF, that is equals to W1 into X1 plus W2 into X2 plus W3 W3 into 0. So this will be your 0, so W3, right? So this is for solute and this is for the solvent, right? Whichever thing is possible for you, you can calculate using that thing, right? So this is how we perform the this particular metal balance in the crystallization unit. One more thing that is very important, so sometimes in the problem they will give you how to calculate the mole fraction of solute in the crystals or hydrated crystals, right? If it is given like that, then how can you calculate? So it, let's say uh, we have to solve some particular problem on that, then only you will be able to understand that thing. So in the next lecture I'll be talking about calculation of the mole fraction in the hydrated crystal for the solute, and once we solve some numericals, then you will be able to understand how actually we can incorporate this kind of problem in the actual chemical engineering problem. Okay, thank you all for attending this lecture. See you in the next lecture. Stay tuned.